Okay, this is the last portion of the lecture covering Newtonian gravitational potential energy. When it comes to exploring the solar system, the hardest part about doing so is frankly getting off the Earth. Once you get off the Earth, which as you'll see requires a large amount of energy, then it's relatively easy to go elsewhere in the solar system. The hard part is getting off the Earth, however, in the first place. So let's say, for example, that we want to launch an artificial satellite from the surface of the Earth into uniform circular motion above the Earth. We want to do so with a sizable payload, say 100 kilograms. So then therefore, how much energy is necessary to launch such a satellite into uniform circular motion if we want to put it at a specific altitude above the ground? So let's take a look at the following example, copy it down into your notes. How much energy is necessary to launch a 100 kilogram satellite into a circular orbit 500 kilometers above the Earth's surface? Once again, for simplicity, we'll ignore the Earth's rotation. Okay, let's begin to think of the problem in the following way. Okay, now right here we'll say is the Earth, right here is the center of the Earth with mass m sub b, and then right here is our satellite initially at rest on the launch pad. So the initial speed v0 is equal to 0. And then what we do is we fire our engine like so, launch the satellite into orbit, and then we cut off the engine at just the right moment when the object is 500 kilometers above the ground and it has a speed v. It has a speed v such that it coasts at this point and it ends up in uniform circular motion about the Earth forever. It's in orbit, so then therefore it does this. Like so, from this point forwards. So how much energy is necessary to do this? Okay, let me go ahead and label a few other things on the diagram before we begin. Right here is the radius of the Earth, and then right here is this distance r, which is equal to the radius of the Earth plus the altitude of 500 kilometers above the ground. So let's go ahead and write down some numbers. So we have, first of all, capital G, which is as follows. Okay, we're going to need the mass of the Earth as well. That's this number here. We'll need the radius of the Earth. That's 6,400 kilometers, 6.4 times 10 to the 6 meters. But then we also need small r. Small r is equal to the radius of the Earth plus 500 kilometers above the ground. So it's 6,900 kilometers, which is 6.9 times 10 to the 6 meters. Okay, now if we ignore the mass loss that occurs in this problem as you fire the rocket engine, then we'll just treat the problem in the following way. Think of us firing the rocket engine as like a non-conservative force. Think of it as like a push, if you will, that's going to push the satellite of mass m equal to 1 kilogram. I neglected to write that down earlier. 100 kilograms, excuse me. It's going to push the satellite of mass m equal to 100 kilograms, initially at rest here on the surface of the Earth, up into this orbit such that it's in uniform circular motion. So we'll consider that push from the rocket engine to be a non-conservative force. So then therefore we'll calculate the work done by the rocket engine. That is then therefore the energy necessary to do this. So then therefore we set up our expression in the following manner. Recall that the work done by a non-conservative force, in this case the work done by the engine, results in changes in kinetic energy plus then changes in gravitational potential energy. So what we have to do basically is just fill in all the terms here on the right hand side of the expression and then just calculate it all out, and we'll end up with a certain amount of joules. That's the amount of energy necessary to do this. Okay, let's just start going ahead now and filling in our terms. So first of all, the change in kinetic energy. We're going to have a final kinetic energy here with this speed v. The speed v is not given in the problem, but we do know how to calculate it by setting up F equals ma. We'll do that in just a few moments. But for now, the final kinetic energy is 1/2 mv squared, then minus the initial kinetic energy of 0. Remember, we're ignoring the Earth's rotation for simplicity. Okay, and then we have changes in gravitational potential energy. Let's just be careful of our negative signs here. I'll do this on the lower board. The final gravitational potential energy is the following value when we're at position small r, and then minus the initial gravitational potential energy like so when we begin at the surface of the Earth. Like so. Okay, let's go ahead and start to simplify a little bit. First of all, these negative signs will cancel to give me a positive sign like so. But then nothing else will cancel from the expression. The mass m does not cancel from this expression because the left-hand side of the expression is unknown. It's not equal to 0. This is, once again, what we're trying to find. Now, in order to calculate all of this out, however, we need to know what the speed v is. We can find that, as I said, by doing a little bit of F equals ma when the object is in uniform circular motion. So briefly go back to our unit on gravitation. When the satellite is at this position, the force of gravity exerted upon it due to the Earth is as follows. Gmm over little r squared. This then equals mass times acceleration, mv squared over r, because once again the satellite is in uniform circular motion. So now I'm going to go ahead and cancel out an r here and here, and then I'm going to take this expression 4mv squared, gmm over r, and I'm going to plug it into there. And then we'll simplify and calculate out everything. Okay, so let's go ahead and adjust this expression now. So the work done by the engine is going to be, first of all, 1/2 mv squared. So 1/2 gmm over small r. Okay, and then minus gmm over small r. So we'll be able to simplify here in just a moment. But then plus gmm over big R. Like so. 1/2 minus 1 is -1/2. So let's go ahead and simplify once again. Like so. And then before I plug in my numbers here, this is somewhat of a laborious calculation. I'm going to do one extra step to make the process as easy on myself as possible. Let's go ahead and pull out the gmm, which is common to both terms. Let's go ahead and put it out in front like so. And then here's what I have left over. This expression here, like so, and now we plug in our numbers. When I do plug in my numbers, I should end up with a positive number because it's the work done by a pushing force, if you will, that's pushing the satellite up into orbit. So let's go ahead and work this all out. I'm going to do the brackets here first. So -1/2, and then I'll divide by 6.9 times 10 to the 6th, and then plus 1 over the radius of the Earth. Okay, and then I take what I have here in brackets and multiply by these guys. So times 6.67 times 10 to the minus 11 times the mass of the Earth. And then multiply by 100 kilograms for our payload, as it's called, for this artificial satellite. And you end up with this huge number. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's about 3.35 times 10 to the 9th joules. 10 to the 9th is a billion. So we're talking about multiple billions of joules to take something that weighs a couple of 100 pounds and then throw it up into low Earth orbit. Once again, the hardest part about getting off the Earth is using all of this energy that is necessary to do so. Once you get up there, however, then it's relatively easy to go anywhere else in the solar system by using, for example, say, a Hohmann transfer orbit, which I covered in the previous lecture. Okay, that completes this short section on the unit here, or in the unit, that is, for Newtonian gravitation, potential energy associated with it.